Welcome back, everyone. I want to continue our discussion on PLCs, programmable logic controllers. In the last video, we did an overview of the PLC. I showed you a picture of a PLC, and we pointed out that most PLCs are modular, meaning that they have these individual pieces that can be removed and replaced. So you had the I/O section. Those are individual modules that you can pull out and put in. You had the CPU or the controller module. There was a communications module. So there's these pieces that make up the PLC. And what we want to do now is talk more about those pieces, those individual pieces. In this video, we're going to talk specifically about the PLC's CPU, the Central Processing Unit. The way to think about the CPU or the CPU module is containing these subsections shown. There is the microprocessor, which is actually, think of it as a tiny computer. It's the heart of everything in any digital device. There's memory, and then there's power for the microprocessor. Now notice the direction of these arrows. So this power supply powers both the microprocessor and gives power to memory. And here I have an arrow going from the processor to memory, and from memory going back to the processor, indicating that there's communication between the microprocessor and memory. I have bits going back and forth between these two subsections of the PCU, of the Central Processing Unit. We did mention in the live stream, if you were present for the live stream or looked at the video yesterday, that when you have digital information stored as bits, we store those zeros and ones, and we mentioned the fact that we actually store voltage levels. We talked about storage of bits, but we also talked about how you would move bits back and forth between maybe, let's say, a computer and a printer, and I also gave the example of maybe moving those bits between a microprocessor and memory. So here you can actually see in the Central Processing module, Central Processing Unit, an application of what we talked about in that live stream. Now in this class, even though we understand the microprocessor to be a part of the CPU, often I'm going to use those two terms interchangeably. So for this class, for the purpose of this class, we're going to consider the microprocessor and the CPU as the same thing. And if for some reason I need to be more specific about the difference between the two, I will bring that out. One important thing to understand, any CPU are going to have what we call modes of operation. And for you, the two important modes are the run mode and the program mode. Now, I'm going to provide a link somewhere on Canvas. It'll be clear to you where it is. It's a link I want you to go to. I'm not going to talk about it in this video or in class. I want you to go to the video, to go to the URL and look at the web page on these modes of operations for PLC, so you can understand a little bit more about it. But for us, the run mode and the program mode are important. So here's another way a PLC differs from a regular computer. If you ever had a chance to program a computer, you turn the device on, you bring up some kind of application, and you start typing in the keyboard. And then you save it, and you may debug it, and eventually there's a way to run it. Well, you can do the same thing with the PLC, but with the PLC you have these modes. So if I move this switch from run to program, that allows me to enter a program, and the program we're going to enter is going to be very similar to that ladder logic that I showed you in the live stream. So you would enter that program, and once the program is entered, you want to run it to make sure it works. So then you would move the switch from the program mode to the run mode. Before any of that's done, though, a big difference between a PLC and a regular PC is that often PLC will have actual memory in the programming device itself. For example, the PLC that I usually bring in the class when we meet face to face has a programming device that has its own memory. So when I enter the program, I'm entering the program into the programming device, not to the PLC. In order to move the program, once I get the program entered into the programming device, in order to move the program from the programming device to the actual CPU or PLC, I have to download the program. There's a button that says enter on the device I have, and on your simulation software it says download. So when you program, you would have, if this were the button that you use, you would have this button or this switch in the program mode. It will allow you to program, to enter your ladder logic, enter your program, and then you would move the program from the programming device to the actual CPU, and then you would change this, you would switch this to the run mode, and then you can run. When you're in run, you cannot edit, and when you're editing over here in program, you cannot run it. And that's, hopefully you can see why that would be necessary, since this thing is actually going to be automating systems, and in some cases large and dangerous systems. What are some of the functions of the CPU? Well, one important function is that it executes the operating system. Now, what is an operating system? Well, you guys are probably familiar with names like Windows 10. I'm not really that literate with cell phones, but I know there's Android cell phones, and then there's Apple cell phones. You've heard of operating systems like Linux or Unix. Windows have their own operating system. So what is the operating system? Well, let me back up and talk about software in general. What is software? Software are the programs that you either use or that are used to run the computer. There's two types of software. There's application software, and then there's the operating system, which we're talking about here. Application software is any software that you as a user interact with. So for example, right now we're looking at PowerPoint. That's an application. I interact with the PowerPoint. I click the slide back and forth. You may have a cell phone. You download some kind of app, maybe a bank app or whatever kind of app you interact with. That is app is short for application. So the user, you as a user, you interact with the software called an application. That software, the application, doesn't have access to the machine hardware directly. There's another layer in between. If you think of layers, the lowest layer in the computer or digital device is the hardware. The hardware is stuff that you can touch. So in between the hardware and the user, you the user, are a couple of layers. You interact directly with the application. So maybe it's, let's say, Microsoft Word, just as an example. Well, let's say you hit the print button on Microsoft Word. Microsoft Word does not interact directly with the computer hardware. It's this operating system that's a layer in between the application software and the actual hardware. So one of the jobs of the operating system is to execute commands that are received from the application software that is running. The CPU manages memory, and we'll talk more about what we mean by memory management. Monitors inputs and outputs, evaluates the ladder. The ladder is, again, I showed you a ladder logic diagram in lecture. I showed you a simple ladder, and so it turns out that ladder is actually very similar to the programming language that we're going to use to program our programmable logic controller. And so the CPU will evaluate that program, and that program is called ladder logic. So it says here evaluates the logic. The ladder diagram is referring to the ladder logic diagram. And then it turns on and off the outputs according to the program that you put in. So if we go inside of the CPU, there was that one section called memory. Now let me back up and say that there are going to be two documents on Canvas that you want to make sure you look at. I'm not going to go over them, but you are responsible for the information on those two documents. The first one is a memory. It's called memory types. I want you to look at that. There's different types of memory. We'll talk about two. but there's different types that you want to be familiar with, and that's in that document called memory types. And then there's a second document called specifications. So look at both of those before the first exam. You're responsible for everything in those documents, so look over everything in those two documents, and if you have any questions, I'll take the questions, but I'm not going to talk about those documents specifically. Now, memory. It says here, memory is where the control plan or program is stored in the PLC. The information stored in memory relates to how the input and output data should be processed. Now, there's different types of memory, and let me say, and I'm sure most of you understand, there's a difference between memory and storage. So storage is where you keep things long term. So your flash drive would be storage. Your hard drive would be storage. Even the cloud is storage. Memory usually is where you keep things kind of short term. So I mentioned that there's two types of memory that you should be familiar with. Well, actually one type you should be familiar with, but two types you probably heard of. One is called RAM, R-A-M, RAM, and the other is called ROM, R-O-M, ROM. And RAM stands for Random Access Memory. ROM is read-only memory. And let me say that all memory is random access. Doesn't matter if it's RAM or ROM. All memory is random access. And what does that mean, random access? Well, random access means that you can access all parts of memory in equal times. That hasn't always been the case. Back in, I don't know, probably the late 50s, early 60s, they used tape, like cassette tape, something similar to cassette tape, as a memory, and the tape will spin backwards and forwards to find the bits that you're looking for. And so there was kind of a sequential thing. If you had information that you needed on one end of the tape, it had the spindle would have to rewind to get those bits and then go back and forward to access the information. Well, that's not the case anymore. We have random access memory, which means I can get to all those parts of memory, all those bits in equal time. So what is ROM? ROM is read-only memory, and the difference is, and I think we go more into this later, so I don't want to get ahead of myself, but the ROM basically is when you can't write to ROM, you can't store anything on ROM. It's kind of pre-programmed and from the factory, and it has the purpose of ROM is mainly to start the machine. So again, I don't want to get too far off track and go into details of something that we're going to talk about later. So we'll just think about memory. We'll keep it simple. We'll think of it as this box I have right here, and it says this is where we're going to put our control plan or our program, and then we'll get into a little bit more detail about what I mean by control plan program in just a second. Here are some very, very important terms. Please mark this slide. Use this for studying. I will definitely ask about this on a test or quiz at some point. You want to be very familiar with these words, the first few bullet points at any rate. The first one we've already talked about, a bit. A bit is a binary digit. So a bit would be a 0 or a 1. A byte. A byte is a group of bits. It's a fixed number of bits. 1 byte is equal to 8 bits. Now there's also another one I don't have on this list. You can have a half a byte, and that's called a nibble. Like a fish, if you go fishing, you might get a nibble. A half a byte is called a nibble. You don't really see that too often. The reason you don't is because in most machines, the smallest piece of information you could access is a byte, 8 bits. That's not true with PLCs. We can go smaller with a PLC, but in most other machines, 1 byte is the smallest piece of information you can access. Kilobyte. Now it says here, if you look here, it says, notice the kilobyte, KB, capital K, capital B, versus KB, capital K, lowercase b. What's the difference between these two? Well, if they're both capital, that's kilobyte. If I have a capital K and a lowercase b, That's kilobit. Now this gets a little bit, it can be a little confusing because you know, you guys being engineers and engineering technologists, you know kilo means 1,000. Well, in the world of computers, if we're talking about kilobytes, a kilobyte is not 1,000 bytes. A kilobyte is 1,024. And the reason is that when we deal with computers, as you will find out next week, everything is based on powers of twos, a power of 2. And I'll go more into that in detail next week when we talk about number systems. But understand the difference between a capital K, capital B, and a capital K, lowercase b. If they're both caps, that's kilobytes. If the B is lowercase, that's kilobits. Now, when I'm referring to kilobits, which you don't really refer to that too often nowadays, it's usually kilobytes. Kilobits was big back in the early days of computing. They used to use something called a modem for computers to communicate back and forth, a modem through a phone line. And those modems would transmit the bits in a serial fashion. We talked about data transfer in our face-to-face, in our live stream yesterday. And so go back and look at that if you didn't have a chance to do that. But you know, one way to move bits is I can move them bit by bit, kind of down one line, and that's called serial data transfer. And so when they talk about kilobytes or kilobits, when modems were popular, since they were sending these bits out in a serial fashion, the number of the thousands of bits that you could send a second would the higher that KB, the bits per second, the better modem you had. So the thing to know here, though, I don't want to confuse matters. Most of the time we're talking about kilobytes. But if I'm talking about kilobytes, the kilo means 1,024. If I'm talking about kilobits, then the K means 1,000 as you're used to. So you want to make sure you're clear on what I just said. If you're not, please ask me during the live stream, because what you're going to have to do for me is a memory calculation at some point, either on the quiz or exam. So a bit is a binary digit, a 0 or 1. A byte is 8 bits. We talk about kilobytes. Kilobytes is one kilobyte is 1,024 bytes. So if I said you have a system that's I don't know, let's say 10 kilobytes, how many bits is that? You'd have to figure out the math that could go from kilobytes to bytes. 1 kilobyte is 1,024 bytes. And then from bytes to bits, a byte is 8 bits. You can do the math and figure that out. So, bits, bytes. This next one is called a word. Now, a word is a little different than a byte because a word, the size of a word is not fixed. The size of a byte is fixed to 8 bits, but the size of a word, it says here a word can be 1 byte, which is 8 bits. A word can be 2 bytes, 16 bits. A word can be 4 bytes, or it can even be more. Basically, a word is machine dependent. Now, what does that mean? Well, being machine dependent means that whoever designs that machine, that computer, that phone, they have control over the size, the word size. They can make a 32-bit word if they want to. And that's important to know because as someone asked in one of the lectures, the actual word size dictates in a lot of cases some of the physical construction of the machine. For instance, in our class, we're going to use a 16-bit word. Well, what that means is your input module or output module is going to have 16 terminals you can connect to. Your input-output table, image table that we talked about, there's going to be 16 rows there that can store bits, and so that becomes very important. So a word is machine dependent, but for the purposes of our class, we're going to assume a word is 16 bits. So make sure you're clear on that. In reality, a word, how big is a word? Well, it depends on the machine. Whatever Microsoft or Apple, they can make the word size whatever they want as long as it's a power of 2. For our class, we're going to assume a word is 2 bytes or 16 bits. This memory location or address, we'll say more about that in a future PowerPoint. This memory utilization, one location per coil or contact, that kind of refers to the fact that if you remember when we talked about the relay consisted of basically two main parts that we talked about. We talked about the coil and we talked about the contact. Now that coil can either be energized or not energized, and that contact can be open or closed. Therefore, we can use a single bit to represent both of those. We can use a single bit to represent a coil being energized or not energized. Maybe if the bit is a 1, that stands for a coil that's energized. If that bit is a 0, that means that coil is not energized. And we can use that same kind of thing for a contact. If I have a 1, that could indicate a contact is closed. If I have a 0, that could indicate a contact is open. And so we'll get more into that. When you understand the information we talked about in the last couple of videos, we talked about digital stuff and binary, and you'll see how we actually use these bits and bytes to mimic things in the real world. That's the importance of understanding the digital conversation that we had in week 1 of the course. And finally, these last two memory terms, volatile memory versus non-volatile memory. Where earlier I mentioned two types of memory, ROM and RAM. Well, RAM is random access memory, but that is volatile memory, whereas ROM, read-only memory, is non-volatile memory. And volatile memory, all that means is, if it's volatile memory, if you have information in the memory, if you have zeros and ones stored in that memory, you must have power applied to the memory to keep that information there. So, example, let's say that you're typing the letter and you use Microsoft Word to type the letter. You type in the letter, and before you have a chance to hit the save button, your little brother runs and trips over the cord and unplugs the computer, and it goes away. So you plug it back in and you reboot the computer, and the letter that you typed is disappeared. Well, why did it disappear? Well, you didn't save it. Well, what do you mean by save it? When you save a document, what you do is you move it from RAM, random access memory, to the hard drive or to some other storage device. So ROM will hold that information as long as it has power. If you remove power, whatever bits are stored in the ROM, they're gone. They disappear. So ROM is volatile, meaning that if you remove power, the information inside of that memory is lost. I said ROM. RAM is volatile. I'm sorry. RAM is volatile memory. ROM is non-volatile memory. So let me back up so you're not confused. So any memory that's volatile, if it has information stored in it and I turn the power off, that information is lost forever. If I have memory that is non-volatile, the memory, when power is removed, whatever contents that memory has, it'll keep that contents, and the next time you turn it on, it'll still be there. You can see why ROM is important, that ROM is non-volatile, because when you boot up your computer, the way the computer knows how to boot up has to be stored somewhere, and if memory require power, well then that you wouldn't be able to use RAM because it requires power, so you couldn't store the information there. You need some kind of memory that will hold information, so when the thing turns on, it can look at that information and know how to boot up. And that's why ROM is non-volatile. Let's go in the memory a little further. When we think of memory, I want you to think about it like this. These three sections. Now, in reality, permanent storage and memory are two different things. Permanent storage, as I said before, permanent storage might be like your hard drive. Memory is like RAM. You type in the letter, it's in RAM. When you save it, you move it to the hard drive. We're going to consider for this class, we're going to consider permanent storage and memory to be all one thing, just to keep it simple. So I want you to think of memory as these three sections. You have permanent storage, you have the input image table, and you have the output image table. We actually talked about these in a previous, I think it was a couple days ago, we talked about in the live stream. Or it might have been, I don't know, it might have been the last video. But anyway, I showed a document, and that document had two tables on it. One was called the input image table, and the other was called the output image table. And it had this weird numbering system that we'll talk about at a later date. So for now, the input image table will basically keep track of the inputs. If those inputs are switches, if those switches are open or closed, it'll keep track of that. The output image table will keep track of, depending on what program you put in, it'll keep track of whether those outputs should be enabled or disabled. And we'll get more into this a little later. So once I explain the input and output image table, we look at that a little closer, this will make a little bit more sense. Now I think I mentioned this in our last stream, but when you guys actually use a simulator, you will not see the word input image table or output image table. In the simulator that you use, they call these tables data tables. So the data table in the simulation software is the same thing we're talking about here, but we're calling these input image tables and output image tables. I think data tables are a little easier to see. Okay, well, how do these tables work? What exactly do they do? Here's a input module. Remember, I have those screw terminals that I can connect wires to, and I have the switches here. I got a switch down here, and that switch is open. I have a, looks like a normally closed push button here. I got some kind of push button here, and that switch is closed. And these arrows mean that I have a wire connecting that button and that switch to one of those screw terminals in the input module. So this is all hardware. This is all hardware. Over here on the right side of the screen, this is all software. This exists in memory, which means it's not real. It's just what we call a virtual logical structure. This is a way to think about memory. So you think about the input image table as this table. Now, remember when I said earlier that a word for us, a word size is machine dependent. We're going to assume a word is 16 bits. If a word is 16 bits, that's going to dictate how our modules are constructed. If our word size is 16 bits, that means our registers are 16 bits. And remember, a register holds those zeros and ones. That means we're going to have 16 screw terminals that I can connect to. And if you look, if I got this right, you should have 16 rows here, or 16 positions here in each row of this input image table. Now, think of these as cells. Now, you see zeros and ones there, but think of these as cells. And the cell can basically contain a 0 or a 1. It cannot contain anything but a 0 or a 1. Well, it turns out that each of these, if I have, say, 16 screw terminals I can connect to. Now remember, in digital, we don't count starting with 1. We don't go 1, 2, 3, 4 all the way through 16. We start at 0 and count from 0 to 15. But I would have 16 connection points here, and I would also have 16 spaces or 16 cells in the input image table. Now remember, this is all software. Well, each one of these screw terminals map directly to a position in the input image table. And so I have this arrow here. I have this blue arrow coming over here pointing to that bit right there. So what that's trying to indicate to you is that this screw terminal that this wire is connected to is mapped to this bit position in the software in the input image table. And since this switch is closed, there's going to be a 1 there indicating the switch is closed. Notice that the contact here is open, so if I follow this over here, this line, this screw terminal, whatever number that is mapped directly to this bit position in the input image table. And since this switch is open, there's a 0 there. If I were to open this, that 1 would change from a 1 to a 0. If I were to close this 0 would change from a 0 to a 1. It would not do it instantaneously though. In a previous discussion, we talked about something called scan time. Well, it turns out that PLCs, they run in a loop. They scan through a loop, and we'll talk about the process of PLC scanning. You'll understand more about it. But that change, the point I'm making is that change is not instantaneous. The PLC has to go through certain steps, and it kind of goes in the circle. When it comes back and looks at these again, if that switch is closed, if it's changed a state for me, open to close, then it'll update this and change that from a 0 to a 1. Alright, well, we have the same kind of thing with the output image table. So the output image table, now what it will do is it will, to kind of run through the whole thing briefly, you have a switch that's open or closed, right? You have a switch that's open or closed, and depending on whether it's open or closed, that's going to put a 1 or 0 in a row of the input image table. Now you wrote a program that's going to look at that input image table, and depending on if there's a 1 or 0 in the input image table, and depending on the program that you write, it's going to either put a 1 or a 0 in a row of the output image table. And if it's a 1 in the output image table, then whatever screw terminal is mapped to that 1, it's going to turn that device on. If there's a 0 in the output image table, whatever physical output, now remember this is memory, but all of these hard memory connections are mapped directly to a place in memory. All of these screw terminals, which is this is hardware, is mapped to a location in this output image table, which is software. So we'll talk more about what happens in between, and that'll help you to understand better the operation of the PLC. Well, that's it for today. This is a short video lecture, and I only have one. I think in the last video we went over 2 PowerPoints, but this is it for today. If you have any questions or comments about any of the information that I went over, please send me a text or email me, or if we need to do a live stream to answer questions, I'll be willing to do that too. Guys, have a great rest of the day, and I'll see you soon.